everyone. Today we're going to learn how to write electron configurations. A review about electrons. Electrons are negative and are very small compared to the protons and neutrons that are located in the nucleus. The electrons are located outside the nucleus in energy levels or orbitals. Electrons are the particle that is removed or added when ions are formed. Bohr is best remembered for being the first scientist to come up with an orbital theory for electrons. The idea that they are housed in energy levels that have discrete energies and can jump between these orbitals when energy is either released or absorbed. His model often looks like planets orbiting a solar system. A model of carbon is shown here to the right, where carbon has 6 protons and 6 neutrons in its nucleus and has its 6 electrons in orbital paths. There is one problem with this model. Our world is 3-dimensional, not 2-dimensional like this image, and so the orbitals are much more complicated. The principal energy levels, aka the rings from Bohr's model, actually are split into multiple pieces, with the number of pieces it is split into corresponding to what number ring it is. So for example, the third energy level has 3 pieces. Each of the pieces is a different kind of orbital, and the different kinds of orbitals all have different shapes. Some example shapes for some of these orbitals are shown here to the right, where the s orbital is very spherical, the p orbital looks like 2 balloons that are tied together, the d orbital looks like 4 balloons tied together, and the f orbital looks like even more balloons tied together. These are only examples. The d and f orbitals have additional shapes that are not shown here. So what is an electron configuration? An electron configuration is a way of keeping track of which set of orbitals an electron in an atom or ion is located. This is unlike orbital diagrams, which we'll discuss in a later lecture, where the electron configuration will not distinguish which of the orbitals in the set an electron is in, simply that it is in the 2p orbitals, even though there are in fact 3 different orbitals being counted there. There are some important rules and limitations to keep in mind when constructing your electron configurations. The first is that the ground state configuration for any atom or ion follows the Aufbau principle. Aufbau is a German word that roughly translates to build from the bottom. The idea is that the lowest energy orbitals available will be filled before those that have higher energy, because the goal of all of chemistry is to achieve a lower energy state. Also, each type of orbital can house a different number of electrons in its set based on how many orbitals there were in the set. S orbitals can hold up to 2 in their set. P orbitals can hold up to 6 in their set. D can hold up to 10, and F can hold up to 14. Another thing to keep in mind, as mentioned by the Aufbau principle, is that you always fill lowest first, and so there is a set order that orbitals must be filled in. On the diagram here on the right, there are blue arrows to help you follow a path. If you start with the highest available arrow, it runs through the 1s orbital. This is the lowest available energy orbital and will always be filled first. The next available arrow is the one that connects to 2s, so after 1s, you would go to 2s. The next arrow runs through 2p and 3s, so after 2s you would go to 2p, and after 2p would be 3s. This pattern continues onward until the highest available orbital that is possible to fill at this time in the ground state is the 7p orbital. You will notice some orbitals go in strange orders. For example, after the 3p orbital is the 4s orbital, and then after the 4s is the 3d orbital. It is not a guarantee that the number in front always follows right after the other. Sometimes they jump around due to what is called principal energy level splitting. So let us look at what an electron configuration would look like by writing the electron configuration for carbon. We first need to count how many electrons are present. Carbon is atomic number 6, and this is an atom, so it will have 6 electrons. So let us start with the lowest available energy orbital, the 1s. S can hold up to 2, so we will start with 1s2. Currently, 2 of the 6 electrons have a home. We need to keep going because there are 4 more that need a place. The next available energy orbital is 2s. How many can I place in the 2s orbital? Since it is another s-type orbital, I can place another 2. So now we are at 1s2, 2s2. 4 of the electrons currently have a home. There are still 2 more that need a place, and so we must continue on to the next available energy orbital. The next available energy orbital is 2p, and so we will write 1s2, 2s2, 2p2. Note that while p can go up to 6, I don't need to fill all 6 for carbon because there were only 2 more that needed a home. So carbon's complete configuration is 1s2, 2s2, 2p2. You'll notice the superscripts here that count the number of electrons in the orbitals adds up to 6. 2 plus 2 plus 2 makes 6. Let us take a look at another example and one that is a little bit longer. Let's write the electron configuration for an atom of iron. Iron is atomic number 26. Therefore, an atom of iron is going to have 26 electrons that we need to find homes for. Following the Aufbau principle, we must start with the lowest available energy orbital. That is always the 1s orbital. So we will start with 1s2. We have found homes for 2 of the 26 electrons. We must now continue adding to the next orbitals in the set. The next is 2s, so we will add 2s2. We now have homes for 4. After that is 2p, so we will put 2p6 since we do need a lot more homes for electrons. We are now at 10 electrons with homes. There are still 16 more to place. We must continue to the next orbital beyond 2p. The next one is 3s, and so we will put 3s2 because again this is an s-type orbital. 12 of the electrons now have homes. We must continue to the orbital after 3s. This will be the 3p orbital. How many electrons can be put in the 3p orbital? Since it is a p-type, we can place up to 6, and since we have quite a few more to go, we will fill it with those 6. We are now at 18 electrons. There are 8 more that still need a home. We must continue to the one that is available after 3p, which is 4s. We now have 4s2. There are still 6 more that need a home. After 4s comes 3d. D can hold up to 10, however, we only need homes for 6 more. The complete electron configuration for iron will therefore be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. You'll notice 2 plus 2 makes 4, plus another 6 makes 10, plus 2 makes 12, plus 6 makes 18, plus 2 makes 20, plus 6 makes 26. All 26 electrons have found a home. Let us look at a third and much more expansive example to test our knowledge of what order the orbitals go in. Let us write the electron configuration for thorium, atomic number 90. We start off in the beginning with the first few orbitals. First is always 1s, so 1s2, 2s2, 2p6. This gets us to 18. There are many, many more electrons that need a home. So let us continue with even more. After 2p comes 3s, so we'll put 3s2. Then comes 3p, 3p6. Then comes 4s for 4s2. After 4s is 3d. We will fill it with 3d10. And after that is 4p, 4p6. We are now at 36. There are still many more electrons that need a home. Let us continue with the next set. 5s2, 4d10, 5p6, 6s2. We are now at 56. There are still several more that need a home, and the fill order becomes a little unusual here because a new type of orbital is introduced after 6s. The next orbital that is filled after 6s is 4f. F orbitals can hold up to 14. And so we continue. 4f14, 5d10, 6p6, 7s2, and 5f2 will be the final orbitals for thorium. If you add up all of the superscripts for this, you will see that there are 90 electrons who now have their orbitals assigned to them. We can also write electron configurations for ions. So let us write the electron configuration of the fluoride ion, F with a -1 charge. Fluorine, the element, is atomic number 9 and has 9 electrons while in its atomic state. However, this is the fluoride ion. It has a -1 charge, which means it has a different number of electrons. In this case, it is an anion, which means it has gained electrons. Specifically, it has gained 1. So the fluoride ion will have 9 plus 1 equals 10 total electrons. This means the electron configuration for fluoride is 1s2, 2s2, 2p6.